Where are you guys in terms of timeline? Are you guys going after Tiana? You don't know. Is there an interesting process? 是不是第三个是他这边来用的？Yeah, which I just hope the two they already have two offer plans. So they have a good place. ECS is a little slower. Yeah, we apply this cost higher. We made actually some ECS Hi. How are you? Good. Well, could be better. Not bad. How are you? You sit here? Oh, your chair? No. Oh, you sit here? Like 5 years old. What's new? I don't know what's new. I guess in India right now. He's in India right now. Yeah, but he's working on them. Is Peter? He was yesterday. Yeah. That's cool. Yeah. That's 3 weeks ago. Oh, really? Oh, okay. No problem. No, I had trouble. Like I go for several days. I didn't make it. Oh, really? Yeah. You really said no, like that. You should look at the but I have yeah. No, I think
hello everyone. So our first speaker is Song Mei. So before his talk, a good news to announce. Song just won the Sloan Fellowship. It's a great achievement. Let's give him a huge round of applause. So floor's yours.
Okay. Thanks for the invitation and thank you all for being here today. I will be presenting a statistical framework for contrastive pre-training, specializing it to multimodal generative AI. So this is joint work with Kazusato Oko, Li Conglin, and Yuhang Cai, a group of fantastic PhD students at Berkeley. So the motivation of this work is just to get amazed by the exceptional capability of generative AI models. Now, these generative AI models can easily translate between different modalities like image and text. For example, if I just prompt in this DALL-E model a description, a text description, and it could just generate this cute image of dog. And if I prompt this vision language model, like the image and initial prompt, and it could generate this text. So this is just some interaction of me with these generative AI models, and many people are amazed by these exceptional capabilities. So while it's an empirical success, and the mission of like MODL is just to understand, like mathematically understand why these models work so well. So next, I would like to briefly describe how these generative AI model are trained and how they generate this image and text. The first step to train these generative AI models is called this contrastive pre-training. When the modalities are image and the language, this is called the CLIP model. It's by this OpenAI paper and this Google paper 4 years ago. In CLIP, well, in this talk, I will mostly use like image and language for the modalities as examples. So notations will be like image and text. So, but this could be more general. So in CLIP, the data set consists of pairs of image and text, a huge set of pairs which are downloaded from the internet. And given the neural network encoders of text and the images, the neural net encoder of image, well, they just map the samples into the representation space. And then people calculate the inner product of these representations to generate this called the similarity score. The contrastive laws aim to maximize the similarity score for paired images and minimize the similarity score for non-paired images. The training parameters are contained in these encoders, so we expect that after training the encoders, well, the image representation and the text representation for paired image and text align with each other. So mathematically, we can think about there are like samples, image and text ID from some joint distribution. We use notation E to denote encoder, S to denote the similarity score. The CLIP loss can be viewed as a K-class classification loss. To predict the similarity score correspond to the valid pair among K number of similarity scores. Here, K is taken to be some large constant. In CLIP, K is just the 32. So one interesting application of this CLIP loss, this CLIP encoders, is this zero-shot classification task. Suppose we have we have trained these CLIP encoders and have this new image classification task where we are given new image and the potential labels. This zero-shot classification gives a classifier by the following. So we first convert these labels into prompts using a user-defined template. For example, the template here is like a photo of this object. And then people take this pre-trained image encoder and text encoder to map these prompts and the image into the representation space, calculate the similarity score, and the classifier just choose the label corresponding to the maximum similarity score. So the interesting here is that, well, the text encoder and image encoder is fixed, is from the pre-trained model. And there's nothing training happening here. So this is called the zero-shot classification. And the interesting thing is that, well, the performance of this zero-shot classifier achieve 88% for the top one accuracy on ImageNet. So here, this pre-trained encoders was not trained on ImageNet. Well, maybe the dataset contain ImageNet, but the distribution is definitely different from the distribution. And it's not specifically trained for this zero-shot classification task, but the performance is very good. This 88% is like the performance of a good ResNet 50 layers and trained on ImageNet achieve this like 88 accuracy. So it's quite interesting result. And also these CLIP encoders have applications in generation tasks. And here, this is like the vision language model where the goal is to generate text from image. So the way to do it is that, well, we use the CLIP image encoder to compress this image into a few tokens and concatenate with the text tokens and use it to train this transformer-based vision language model and train this transformer using the next token prediction loss. After training, well, we just have a new image and the initial prompt will just sample these tokens sequentially using this trained model. And the interesting thing is that, well, people can just take the fixed clip image encoder and just train this transformer and could get a good performance. So a similar story happened in this conditional diffusion model where the goal is to generate the image from the text. So in diffusion model, the way to generate the image is, well, you have an initial Gaussian noise and recursively apply a denoising neural network until the last step, you have a clean image, use it as a sample. And of course, well, the prompt will be used in this as a guidance in this generation. And for each step of this denoising step is given by, well, this map is given by this trained transformer or unit. And the input of this transformer is like a noisy image and the fixed clip text encoder. And output is a clean image. And the way to train this transformer is like use the regression loss on clean image and the output of the transformer to train this transformer. Okay, so this is like how these multimodal generative AI models are trained and how they sample this image and text. So the theoretical questions that I would like to ask, I would like to answer like are the following two questions. Why are these clip encoders effective representations for downstream tasks? And why do encoders and downstream functions admit efficient neural network approximations? So I will answer these questions separately. So let's first go to the question, why are clip encoders effective representations for downstream tasks? So there is a huge line of literature on contrastive learning theory, and here I list a few of them. A few remarkable works include the work of the group of Princeton. They have the first paper studied how minimizer of contrastive loss could adapt to downstream linear classification tasks. And then the group of Stanford, they studied, they analyzed this contrastive, the spectral contrastive loss using spectral clustering perspective. Spectral means like the square type of contrastive loss. And then the group of Columbia and Microsoft research, they analyzed this contrastive learning using the copy modeling perspective and the multi-view redundancy perspective. And while there are many more work on contrastive learning theory, and I apologize if I missed any important work here. So, well, you can see that there are many work on contrastive learning theory, and one question is like how these results are compared, and well, actually these results are not easily comparable. The reason is that, well, the type of contrastive learning results heavily depend on the model assumption, how you assume like the ground truth distribution, especially the connection between the pre-training task and the downstream task. So for different type of assumption, you can get the different results. So these results are really not easily comparable. And well, you can see that our work is based on like a huge line of literature, and we want to like adopt a little bit new perspective on this problem, and we use this problem called this the perspective called this sufficient statistics. And I feel that this new perspective provide a framework that is general enough, and relatively the assumptions are relatively simple, and the results are relatively clean. Okay, so let's first review the concept of sufficient statistics. this is an old friend of statisticians and information theorists. So given two random variables, x and y, and a statistics t maps x to t of x. We say t is a sufficient statistics of x to y if x and y are independent given t of x. In information theory language, we can say that the mutual information of x and y is the same as the mutual information of tx and y. One caveat here is that while this sufficient statistics is the Bayesian version of sufficient statistics, in the frequentist version, y, instead of taking it to be a random variable, is a parameter. It's like a parameter that index the distribution of x. And here, this is the Bayesian version where you can imagine that the parameter theta has a prior distribution, and then you can have this definition of sufficient statistics.
Just so I understand the sort of types of objects here.
When you say t is a statistic, is this just a function of x?
Oh, it's a function of x.
Okay.
Yes. Yeah.
Cool.
So intuitively speaking, you can view this t of x a compression of x, but contains all the information in x used to predict the y. So what is a connection of sufficient statistics with contrastive learning? Well, here, this is the loss function for the clip, for the contrastive learning loss. And if you do a simple algebra, you can easily get this lemma saying that, well, suppose like the function class is rich enough, the global minimizer of this clip loss could have an analytical expression, which is given by this log ratio of the joint distribution of image and text over the product of marginal distribution of the image and text.
Sorry, what is it again? So this is the loss for the
R of S is a loss function. And yeah.
Just want to unpack this. I never saw it, but so the input is text and images, right?
The input is text and image, yes.
Text and image. And what is S?
S is the similarity score.
Similarity
There
score.
is an encoder of image and encoder of text. S is a function of these encoders.
Okay.
And you train these encoders.
So the parameter is S in the sense,
The
right?
parameter is like the encoders, but you can wrap these encoders in this S. And let's say you minimize the S instead of minimize encoders.
So, okay. So you minimize the parameters that define S, basically.
Yes, yes.
Got it. And what is this S as a black box? Is it important to know what it is? Or?
This S.
How is it dependent? Is it neural network representation or something?
Yeah, let's say the neural network is huge enough, so this S could be arbitrary function.
S is arbitrary.
Yes.
Okay, then I have just a conceptual question. So
yes.
we have this very simple scheme for training. Of course, you want to basically couple images and texts and minimize the score. Right. That's understood. That could have been done well before, like decades ago. And now we have this unreasonable effectiveness of this. To what should we attribute the success? Do we attribute the success to this S as a black box, that the representation that we're not seeing here, that S is so effective, or some other things?
Actually, the S is really effective. I think it should be mostly attributed to like we are minimizing this loss function, and the minimizer is very effective.
Let's say instead of so what is it? Where's the miracle? Is the miracle hidden in S, or the miracle is hidden in how we minimize this thing? Why things work so well?
Yeah, so we will see soon, and we want to explain this using this sufficient statistics perspective. So I think maybe like I can answer a question after introducing the theoretical result, and we will see.
Is that a question that concerns all of deep learning?
Yeah, it's gonna, exactly. It's all of deep learning.
Good question.
That's a good question. But you know, here, yeah, but right. But when we look at deep learning, we unpack deep learning. We say, okay, here's the deep learning scheme. Here's how the parameters. All right, that's understood. But here we kind of hide the deep learning, and so I'm trying to understand whether the success is hidden in S or the success is hidden in somewhere outside S. Yeah. So
perhaps you
yeah, perhaps you will
later,
see soon. Yeah, I think we can discuss a lot after. Yeah.
Are you supposed to have a positive sign on one of those two terms, on the second term? Positive? Yes.
Oh, you are saying like this is typo? I think this should be a negative sign.
So you want to make one of them large and the other one small.
Oh, okay. So the way to view this, well, okay, you can see that there's a numerator. There's a numerator and denominator. You want to maximize the numerator. You want to minimize. You want to maximize the numerator and minimize the denominator. That's the way to think about it. So you want to maximize these two things and minimize the others. Yeah. Right. So this is like the minimizer, the global minimizer of the clip loss. And there is a straightforward corollary of this formula, which says that, well, the clip minimizers are just sufficient statistics. So suppose this minimizer is achieved by a function of image encoder and text encoder. And suppose this function can obtain the global minimizer of this clip loss, then these pairs, like the image encoder and the text encoder, are pairs of sufficient statistics. So the way to see it is like you manipulate here this formula to reformulate it so that you can see that the probability of the image given the text is the probability of the image multiplied exponential of this similarity score, and apply a very classical result in theoretical statistics called the Fisher-Neyman factorization theorem. You'll see that, well, the text encoder is a sufficient statistics for predicting the image, and symmetrically, the image encoder, well, if you manipulate it in the other way, the image encoder is the sufficient statistics to predict the text. So that means like the global minimizer is quite effective. It contains like, well, you can see that the global minimizer actually contains this joint distribution of the image and text, right? So if you are able to get this global minimizer, you get a lot of information on this joint distribution. So this is like the a simple like interpretation of like the minimizer of the clip loss, and all these things are known previously.
So can I have a question?
Yeah.
So it feels like this similarity, it's symmetric in its two inputs.
Yeah, the symmetric. Yeah.
So sufficient statistics like your explanation.
Yeah.
So seems to suggest like image is sufficient. The encoder of image is sufficient for predicting text, or
right. The image encoder is sufficient for predicting text, and the text encoder is sufficient for predicting an image.
Okay.
Actually, I have a follow-up question. No text is going to be good enough to predict an image, right? I mean, I cannot describe an image only with a text description.
Yeah, so there's a joint distribution, so there's still randomness, but I'm saying like you can use it to generate the text. You can still use it. You can use it to sample this distribution, and that is sufficient.
So the amount of information in the caption is limited,
Yeah.
but the encoder, the text encoder of that caption contains all the information that's there.
So I think, yes, I think the information is about the distribution, not the realization.
Yeah. I see. Okay. Interesting. By the way, this is true also for logistic regression.
Yeah, it's true. Yeah.
Yeah.
So it's like a simple kind of thing. Yeah. Okay. So what's the implication of this sufficiency? Well, the implication is that, well, suppose you get the global minimizer, then there exists this mu hat as a function of this image encoder, such that this is sufficient to represent the conditional distribution of text given an image. If you get an encoder of the text, this is sufficient for getting this conditional denoising function denoising this image given the text. So this is just a simple corollary. So it means like these are sufficient for these conditional diffusion models and the vision language models. So this is a very simple or elegant story, but there's like a limitation of this thing. When we come to like learning theory, it's required that this obtain the exact minimizer of the clip risk. So the question is like, does this theory generalize to clip empirical risk minimizers? So in learning theory, we care about like finite sample and the efficiency kind of things. So whether there's an approximate version of this result. And our answer is yes. So we can generalize this notion of sufficient statistics to the approximate version of it. And well, we define for statistics, we define the so-called sufficiency measure of statistics. Actually, the definition is also very simple. Well, given two random variables and the statistics as a function of x, we define the sufficiency measure to be, well, there are three different forms, but they are equivalent. If you use the simple information loss form, this is like the mutual information of x, y, subtract the mutual information of t, x, and y. So you can see that the traditional sufficient statistics is just that these two things are equal. So that means traditional sufficient statistics are zero sufficient. And equivalently, there is this variational form for that defining this sufficient statistics, where this is the inf of a risk function, subtract the inf of a risk function, and the risk function, you can see that this is related to this contrastive loss function. And this sufficiency actually is related to the excess risk of the clip loss. And the third equivalent definition is just the, well, this is the expected KL, the expectation of the KL divergence between Py given X and Py given Tx. So a small sufficiency will imply that the Py given X, this conditional distribution is close to Py given Tx, just using the Tx to predict Y. So these measures are close.
Can I ask a clarification question? You're assuming there's a joint distribution between the image and the text.
Right.
So implicitly, you're assuming that deep learning is enough to capture the joint distribution. Is that kind of hidden there?
Currently, yes.
Yeah. So that's also assumption.
Right. The assumption the neural network is powerful enough to capture this distribution. And I will answer this question in the second question.
Thanks.
So this is the first question. Now we assume neural network is powerful enough. All right, so these three definitions are equivalent. You can see that actually this object is just mutual related to, mostly just the mutual information between X and Y, the variational form of mutual information, and this conditional KL is like the conditional mutual information of X, Y given Tx. So by some simple algebraic manipulation, you can show that they're equivalent. But why I just write down these three forms altogether? Well, because like the first definition is related to the traditional definition of sufficient statistics. The second, you can see that it has connection with the clip loss function. And the third one, you can see that it can give guarantee for downstream tasks. So, well, you can easily show that this sufficiency is controlled by the clip excess risk. So suppose there is a S hat, which could be an approximate minimizer of the clip risk. It's a function of the image encoder and the text encoder. The sufficiency of the image encoder plus the sufficiency of the text encoder is controlled by the clip excess risk. So here, well, this is a clip risk. Well, this is the clip risk minimizer. This is like the risk of this S hat. The excess risk will control this summation of the sufficiency. And we can define the sufficiency of this S hat to be the limit of this, the k goes to infinity limit of this excess risk. And also this sufficiency of S hat is an upper bound of the sufficiency of like each individual. You can see here the theorem is not so is also very simple. It's like just a few algebraic manipulation. So we can use this theorem to explain like, well, this sufficiency could control the risk of downstream tasks. For example, we look at this zero-shot classification risk. This zero-shot classification task. Suppose we have this image and the label pairs which are from some distribution. And here we make an important assumption, which is that the image is conditional independent on this label given the text. So this will be realized if the label is a function of the text. And the classification rule, instead of using the softmax rule on the similarity score, we use a little bit more a different rule, which is like the softmax on this modified score. And you can see that this modified score intuitively, well, there is this like Monte Carlo kind of sampling thing. And suppose the sample goes to infinity, and actually this is the Bayes rule. So this is a Monte Carlo approximation of a Bayes rule. And if just the number of sample m is just 1, this will recover the original softmax rule. So if you use this Monte Carlo version of the Bayes rule to predict the y, we can show that the excess risk of this zero-shot classification loss is just controlled by the sufficiency plus some term goes to 0 as like the Monte Carlo sample goes to infinity, which is controlled by the clip excess risk. So the proof is by a simple data processing equality. So also like not very fancy.
Let's assume you can sample from the conditional distribution of the text given y.
Right, that is something, that is assumption. So we are assuming that here adding this template is like sampling this text conditioning on this data.
Okay, yeah. So I mean, in practice, it's kind of a strong assumption, right? That you can generate new captions somehow for each image.
Right. So we view this sampling procedure as like adding the template, and well, here this procedure just implies that we have many different templates, and we sample many of them and aggregate this similarity score across these different templates and use a softmax rule for prediction, and it gives this. So after,
can I also ask a question? So you mentioned before that when people applying clip precision model in downstream, they usually do m equal to 1.
Yeah.
In that case, the upper bound is a constant.
Yeah, it's not useful. So
how do we make sense of this gap?
So the way I understand is that well, if you just use one of them, you want some good concentration happen for this average. So maybe like a sample, a realization of it is like it's like representative enough for the expectation. So yeah, or like in practice, you use one. Maybe like if you aggregate m of them, the performance will be better. So after we finish the paper, we read a paper by a group of Columbia, Daniel's paper, and I just realized that here this theorem is like it's very similar to one of their theorem. So it's a little bit like we are reinventing the wheel. But I think it a bit is like I'm still like very glad that we interpret it through this like sufficient statistic viewpoint, unpacking this the reason why like this zero-shot classification could perform so well. And actually, if you read this paper, this is the multi-view redundancy paper. They actually could relax a little bit this assumption, saying that suppose it's not strictly independent, but allow a little bit well, this is like the mutual information between image and text given the image and the label given the text equal to 0. If you allow an error here, this error will appear in the error bound here. And we can use this image encoder. Well, we can use this sufficiency to control the risk in the conditional diffusion model and vision language model. So remember that in conditional diffusion model, the task is to sample the image given the text, and there is this denoising process. And suppose we have the clip text encoder that is pre-trained. And in diffusion model, it fits a transformer to, given this text encoder, fit this transformer to predict this conditional denoising function, and then generate this image using this denoising function sequentially. So the question is like, why is enough for the denoising function to access this text through this text encoder? So the theorem says that, well, suppose we have a text encoder that is potentially a minimizer of the clip excess, a minimizer of the pre-training risk. Then there exists a function of this encoder that could approximate this conditional denoising function with approximation error controlled by the sufficiency of this text encoder and controlled by the clip excess risk. So one remark is that, well, this is a estimation error bound and also imply a sampling error bound if you use like some Gersonov kind of integration kind of bound, and the same result hold for vision language model. So, well, you can see that for this theorem, well, up to now, we just make an important assumption saying that the neural network class is powerful enough to fit any function. And in practice, these encoders and these denoising function are parameterized by neural networks. So the theorem does not imply that this conditional denoising function can be efficiently learned through the empirical risk minimization over neural networks. So the question is like, why this object admit efficient neural network approximation? So this goes to the second question. Why do these encoder and downstream functions admit efficient neural network approximations? As you can see that if we want to answer this question, we really need a statistical model for the joint image and text distribution. So before, well, we just say there is a non-parametric kind of, well, there is like a general distribution. But if we want to say neural network approximation, we really need a concrete statistical model for the joint distribution of the image and text. So here we propose a very naive process. We call it the generative hierarchical model. It's a tree-structured graphical model where there is a root represent the shared information between the image and the text. And from the root, the tree splits into two branches, the text branch and the image branch. So each branch recursively generates lower level features with a stochastic transition until the leaves are reached. And what we observe are the leaves. The leaves are the text features and the image features. And what we observe are these leaves, the text and these images. And well, what is in the middle here, these nodes are unobserved. And we don't assume that we know the tree structure, and the stochastic transition could be also unknown. So here is an illustrative example of like how this, conceptually, how this hierarchical model generate this paired image and the text. So you can think about for example, the root node is kind of animal, and well, iteratively generate lower level features and generate the image, iteratively generate lower level features and generate the text. So for this model, definitely this is like a non-realistic model, could be much more improved, but we take it as a working model for a proof of concept. This text model, well, people have used this text model. This is related to this like context-free grammar, which is like a tree-structured model. This has been used like since like 1959. When this also has been used in computer vision literature, people propose using this graphical model to fit this image distribution for image generation. And the theoretical analysis of this model was first proposed in the paper by Elkin and Mosio, 2016. And in recent years, this model has been very popular and actively studied. Okay, so the benefit of having this graphical model is that we can show that these functions related to this model can be computed using neural network easily. So for this model, there exists a canonical representation for the image encoder and the text encoder. So this is like the ground truth representation that can compute this similarity score, the ground truth similarity score. So the image encoder is like the probability of the root given the probability of the root given the observed image, and the text encoder is the probability of the root given the observed text. And you can show that these are indeed good representation for this model by looking at by using some Bayes formula for this ground truth similarity score. And you can see that while this conditional probability of the root given the leaf, these are like marginal probabilities that can be inferred using belief propagation algorithm. And the belief propagation algorithm on trees are exact, and you can show that it can be simply easily approximated by transformers. And similarly, like for the conditional denoising function, while on these trees, this conditional denoising function can also be computed using the belief propagation. So you can imagine that there exists a transformer that can efficiently approximate this denoising function. Okay, so given this model, we can get some end-to-end sample complexity results. There are some important parameters for the tree, the depth of the tree, the number of children, the node space size. Well, so here, an important assumption we made is that the node is discrete, which is non-realistic, but hopefully can be improved later. So while there are some parameter of the transformer, but we take it to be polynomial in the size of the problem. And we can show that while suppose we train this clip with function, there exists, well, over this encoder, which the class is over this transformer class, you can get the excess risk of the clip to be controlled by the polynomial of these problem parameters and the scales, and goes to 0 as the sample size goes to infinity and decay as a parametric rate. Similarly, for this conditional diffusion model, if you train the denoising function over the transformer class, while the estimation error will scale with like polynomial of the problem size and the decays in the parametric rate. So one remark is that, well, the interesting is the second part, and this part we didn't use the pre-trained clip representation. So here in this theorem, we assume that this denoising function is trained from scratch. So the input is the text instead of the pre-trained text representation. So one interesting question is like, suppose, well, here we don't train this minimizer, we don't train this like denoising function as a function of the text, but as a function of the text representation, can we still have some end-to-end estimation error guarantee? What happens if we fix the pre-trained encoder using a two-step procedure? So here, these theoretical guarantees are on like, we have like, we train this clip, we get the generalization error. We train the CDM, the conditional diffusion, we get error, but these two steps are not coupled with each other.
Just question. You train the CDM, you train the unit or?
The transformer. There's no unit parameterize every function by transformer.
Transformer, okay.
Yeah.
So you train the transformer.
Right.
So this, okay.
Right.
Thanks.
So I also have a question. So this theorem applies to ERM of the clip loss. Clip loss is some kind of cross entropy, some kind of
right.
So it's a priori unclear why the ERM has to exist. Is there any hidden assumption to guarantee the existence of ERM?
Right. Mostly the result is like a uniform convergence kind of. So there's nothing implicit realization kind of thing here. You can think about this bound is like the uniform convergence bound. So here, this minimizer is assumed to be able to achieved by optimization.
Yeah, so my question is why the ERM has to be finite, has a finite goal?
Well, because we know the population risk. Okay, so or we can just constrain the transformer class.
So you must have some norm bound.
Right, norm bound that is like a polynomial in these parameters. Okay, so there is a challenge to prove the two-step result has an excess response. Well, the technical challenge is the following. So if we want to control the excess risk of the fine-tuning phase, we need to have an approximation of the true denoising function using an efficient network of the learned representation from the pre-training step. This is what we need. We know the true denoising function is an efficient neural network of the canonical encoder. This is because the belief propagation. So you can calculate everything using belief propagation. So you know like the canonical representation is part of the computation for the denoising function. So you can guarantee that the true denoising function is approximately an efficient network of the canonical encoder. The challenge is that while suppose we get an approximate minimizer of the clip loss, we can guarantee that the risks are close, but we are not able to guarantee that the learned encoder are the canonical encoders. And actually, there are many different minimizers that could have this risk bound guarantee. So that means like there's no growth condition on the clip pre-training loss. So that means we cannot just take this N hat to be the canonical neural network. So this is the technical challenge for showing a guarantee for the two-stage results. And this technical challenge is resolved using this theorem. So this theorem says that suppose there is this canonical representation, it's well posed. There are some assumption on this canonical representation, mostly assuming like the representation are full rank in terms of sufficiency statistics is a full rank sufficient statistics. And suppose we have an approximate minimizer of the clip risk. There exists a small two-layer network that can convert any minimizer, any approximate minimizer of the clip risk, of the clip risk to the canonical representation. So the benefit of this result is that, while we can take this N hat here to be the composition of the canonical neural network with this small network. And here, this composition is still efficient neural network. So this is like the way to resolve this technical challenge.
Sorry, can you say a little more about why that's true?
Why this is true? Why for any approximate minimizer of the clip, there exists an efficient neural network to transform it to the canonical representation. Yeah, this is a very interesting thing. So yeah. So the way to see it is that you can see that here you have this equation. Suppose S hat is approximately S star. Well, definitely you cannot show that. Well, this is like kind of a matrix factorization kind of thing. Like the image encoder and text encoder is a factorization of this S star, and this approximate image encoder, approximate text encoder is a factorization of this approximate matrix. So for matrix factorization, you know that there are some like equivariance kind of thing, so that you cannot show this factor is the same as this factor. But suppose but there's a way to recover from the approximate image encoder to the true image encoder by just say, well, we apply the pseudo inverse of this text encoder to this encoder, to this like similarity score. So well, and you can see that applying this pseudo inverse is kind of a two-layer network. So you can just say, well, the network is like you take this as the weight and apply nonlinearity, repair the nonlinear inverse, and apply a pseudo inverse of the text encoder. And of course, this is an infinite dimensional object. So to apply the pseudo inverse, you can use some technique like Monte Carlo sampling technique to to make the neural network from infinite width to a finite width.
So I must have missed this. Is there a constraint that on the form of gamma? Like, does gamma and L have to be simple functions?
Oh, to be like simple, like real to real, scalar to scalar function.
Oh, there's an inner product there. Oh, yeah, I see. Okay.
Yeah.
I see. I had missed the inner product inside there. Okay, that makes sense. Okay.
Okay. So yeah, basically this is like applying a pseudo inverse of this text encoder. You get this small network. So through this theorem, we can get the excess risk of this two-stage procedure. This is an end-to-end result. Suppose we have the minimizer of the pre-training risk and fix this encoder and just train this denoising function as a function of this encoder to get a second, to get this approximate minimizer. Well, the final estimation error of this compositional function estimating the denoising function, well, is controlled by this polynomial of this problem-dependent parameter, and goes to 0 when the number of pre-trained samples and the number of fine-tuned samples goes to infinity in the parametric range. So for this result, it seems a little bit trivial. We didn't seem to like show some benefit of this like pre-training data set, and we leave this as a future open question. But indeed, to get this end-to-end result, I feel like there are many technical challenges. Well, at the beginning of this project, this theorem is what we want. We want to get a fully end-to-end result. There is like a neural network class, and there is this model how we can show the guarantee of this two-stage guarantee, and eventually we get this. And I guess like there's this technical challenge where like this two-stage procedure, why this like minimizer, there is like a efficient network using this minimizer to approximate this denoising function. This is like little bit challenging. Okay, so
can I have a question about the
last result?
So here, if you this is this bound is for the two-step procedure. If you just do ERM on the same function class using just the downstream task data from the downstream task,
right.
What's the risk bound you can get?
So the risk bound is that you just cancel this term, but the polynomial will be different. So definitely, okay, so what you asked is here this theorem. So suppose you just fully train the network, two-stage everything, you get this sound. All right. So we have some, one question is like whether if you do experiment and the minimizer mimic the propagation, so we have done some experiment on toy model with this graphical, the tree structure graphical model with 4 layers, number of child 3 and the node size 10, like this dimension, and we use like the transformer with 5 or 10 layers and the embedding dimension should be this. We train this transformer using a few different approach. The standard TF stands for like transformer trained using the standard loss trained sequentially. Sequentially means like first pre-training, then the fine-tuning. And there is this guided TF, means that we supplement the standard loss by a guided loss, encouraging the model to emulate the belief propagation. So that means like for each intermediate layer of the transformer, we add a loss function to use this intermediate layer to predict the intermediate step of belief propagation. So this is a cheating, the guided TF is a cheating training method. And the shallow TF means that we use a shallow transformer. We want to expect that the shallow transformer cannot perform well. And there's a joint training method where we joint train the clip encoder and the conditional encoder, conditional denoiser. So here, this is the experimental result for the clip training, zero-shot classification, conditional diffusion model, and vision language model. These solid curves are the risk, and these dashed curves are the excess risk. The horizontal axis is a parameter of this ground truth data distribution that control the mutual information between the image and the text. So it's a parameter that control the difficulty of this task. And we want to focus on the red curve, which is like the Bayes performance. So no estimator can be better than this Bayes. And the standard training transformer is this blue curve. Well, you can see that if you don't train, if you just train without the guided loss, there is a gap on the risk. So the dash curve is the excess risk. You can see that it's not super close to 0. If you use a guided way to train it, it performs a little bit better. So you expect because like guided training is like trying to make it mimicking the belief propagation, because we know that the ground truth algorithm could be the belief propagation. And using the guided loss, you can see that the performance is better. And the shallow transformer, and you can see that if you don't use a transformer that is expressive enough, you get a larger gap. And for conditional diffusion model, you can see that while the standard transformer, the blue curve is here, is like even if like we didn't use the guided loss for training the conditional diffusion model, the gap is small. So that is good. And there's a question of like whether the minimizer truly mimic the belief propagation. So we have done some plot some figure when we test the performance in the out of distribution. So that means like the training distribution is different from the test distribution. In this scenario, we don't expect the trained model to perform as good as Bayes, because we expect the trained model to perform like to mimic this B propagation, and we want to see whether this train transformer can mimic this B propagation. We call this misspecified B propagation. Why is misspecified? Because like the training distribution minimizer can have a B propagation, but that B propagation is different from the Bayes because like the test distribution is out of distribution. You can see that the blue, the black curve is the performance of the misspecified BP, and for the train transformer, it's mostly keeping track of this misspecified BP propagation. So this is like an evidence that while when we train this transformer, the behavior is like similar to this. It's just trying to mimic this BP. All right, so let me summarize. We try to analyze this clip model while understand why the minimizer can adapt to downstream task, and we use this perspective called this approximate sufficient statistics to get results, and to get fully end-to-end results using neural network. We propose this like hierarchical model and provide this end-to-end sample complexity for learning this through neural networks. Yeah, this concludes my talk. Thanks for your attention. Happy to answer any question.
It's really interesting to see the sufficient statistic point of view, but I think you attempt to interpret or to explain why this clip might work. So I think another way to show this point of view really explains it is really to see, can you use this point of view to improve algorithm to guide the practice?
Right, that's something we tried to do, and the one attempt we did is like to see whether this like one possible way to use this view to improve this practice is that well, we have proposed this like Bayes kind of rule, like Monte Carlo sample Bayes kind of rule to do the zero-shot classification, and whether this can have a better performance. We did some experiment and see that it didn't. So it's like a little bit disappointing that currently like this, we didn't find a way to improve the practice using this theoretical.
But if you try on your simulated data, would that help?
Oh,
that's an easier problem.
Then that helped. Yeah. So, yes, right. So on we have this. So here, this figure, this is the zero-shot classification figure. So for this zero-shot prediction, the estimator is given by m equal to 100, maybe. Yeah. If you only get m equal to 1, the risk will be large. So on this simulated data, it can definitely help, but on real data, it didn't help.
You probably need to take into account the implicit bias to really bridge the real performance.
Yeah, so yeah, there are many different ways we thought to improve this. One way we thought is like we need to sample this text given the label. So one way to do it is to think about more realistic template to generate the prompt and aggregate them. So we will try that.
Thanks.
I have one more quick question. Thanks for the talk. Just a question regarding like the two-stage train, so the theorem that has both pre-training and fine-tuning. If you can. So, yeah. So here it shows that the pre-training and fine-tuning data, they're almost like symmetric in this. So my question is like, are they fundamentally symmetric in the proof, or there's some assumption that gives you this?
Very good question. Sorry that the presentation seems to make them symmetric, but in you can see they're definitely not symmetric. The polynomial here and here, they are different. I forgot which one is smaller. Hopefully, one hope is that we can use this to show like maybe like, well, use a large pre-training data so that the on top of the fine-tuning the exponent is smaller. Intuitively, this is true, right? Because like this is a parameter counting argument, and the parameter in this m hat is number of parameter in m hat is smaller than the number of parameter in m hat and e hat. So intuitively, like
so the polynomial for the n fine tuning will have some constant that depends on the pre-training as well, something like that, right?
Here there will be a constant that depend on also depend on the pre-training. So hopefully the constant is like small. So we can
our discussion offline. So we have a 22 minutes break. Let's resume our next talk at 11. Thanks.